Okay.
And okay, so so regarding severity, can you give us an example of what type of thing you would want to do with that covariate? How do you think of it, or how do you think it might be useful to answer the questions that you have on your analysis? And we can come up with which particular form of the second level kind of analysis we would need for that.
So I think severity is a covariate that only applies to one of the groups.
Mm-hmm.
So I think it might make the most sense to see just within the stuttering group whether there's an effect of severity in the contrast.
Right.
I'm not sure it would make sense to compare across groups.
Right, and it will be particularly important to see whether any regions that they show as different between the patients and controls, whether within those particular regions you find a correlation between the activation and the level of severity. So you can say something that, well, these patients have higher activation in this area compared to controls, and the more severe the patients have even higher activation than the less severe patients within that same area.
Right, and I also might imagine doing seeing if there's a correlation between bold activity and stuttering severity within a particular ROI, right? So like the cortical basal ganglia sites, or some area that the Godiva model is kind of emphasizing.
Right, exactly. If you have like a priori hypothesis about the regions.
Right?
Right, exactly. You should have a priori hypothesis about which particular regions you might think, or your model might hypothesize that you're going to find some type of correlation between severity and activation. You can actually do the same thing using the same configuration files, but just running ROI analysis so that the analyses are set up on individual ROIs as opposed to across the entire brain. Another thing that you might want to look at, I imagine, is the actual activation within each individual group, right? So you might actually want to look at the difference between novel and learn. You already look at that difference across all subjects, but you might want to, even just as a potential post-hoc analysis, you might want to look at that comparison for one group and separately, and then for another group separately, just to look at those. And the only problem with that is that currently, if you want to do that, it's a little bit complex to specify the contrast. Well, not complex, it's just difficult to explain. Let me actually request remote control for a second so I can just type it.
Would you have to dummy code the group?
Right, because right now, if you want to look at what was the average activation within, what was it, control and patients, the two values of the group covariate?
Yeah.
Okay, so if you want to look at I think it's, let's see, 1 would actually be the contrast that looks at the activation only within the control group, and 2 will be the contrast that looks at the activation just within the patient group. But why this is the case is a little bit complex to explain. So that's why I typically find much better to just recommend people to do that. Basically encode a different covariate or a couple of additional covariates in addition to this group. That is just one covariate for controls and one for patients, so that you can do basically this. It will look like control and patient, and then you don't need these all subjects. It would look like that basically. And then if you want to look at just one group, it can be just that, or even, and if you want to look at the other group, it can be just that. And if you want to look at the difference between the groups, it can be just that, right? So it's simpler to kind of like explain, or at least people don't ask questions if you say that this is the contrast to look at just the activation within controls, and the other one is a contrast to look at the activation within patients. But if you do the whole all subjects and group definition of your design metrics, and you have to enter a contrast that says 1, 2, that's a little bit complex to explain why it is the case that contrast will give you actually the activation within the patient. So I don't know. I would recommend that you just expand that into two separate covariates, at least so that you have the choice to do this type of analysis in a more simple manner. And also, just for reference, there is a very minor difference between doing this. So basically, this is looking at the activation, just at the difference between novel and learn just within the controls, right? But there is a minor difference between doing that and doing this. Just, I don't know why I cannot type twice. So let's see. For some reason, well, I can just go there. My mouse is not Like, you can also do that, right? And that will give you actually also the average activation within controls. Or you could do the opposite. You could just, oh, come on.
Are there any differences between those analyses?
Right, there is a minor difference. You can do that, and that will be the average activation within patient. The difference between this and doing it the other way, I don't know why my mouse is misbehaving. The difference between doing that and doing this is that the average effect that you are measuring is exactly the same, right? So you're looking at the average activation within the novel compared to learn condition just within controls. But t-test actually look at the difference. It's like a ratio measure that looks at the average activation divided by the standard deviation across subjects, right? Like ratio of like a signal to noise ratio is what the t-statistics represents. And in the original case where you are just doing the analysis within control groups, the standard deviation is only also computed within controls, but in this case, the standard deviation is computed across both controls and patients. So basically, the residual error, the denominator of the t statistics value is computed across all of the subjects instead of being computed only within controls. And this is typically a little bit more robust in case, particularly in cases where the subject subpopulations are relatively small, and it's also more consistent with the standard deviation that is actually used in the t-test when you actually compare the two groups. So if possible, I recommend doing it this way. It should be almost similar, almost identical, but not exactly the same, basically.
I mean, is that just sort of like artificially inflating the number of subjects?
Right, but not artificially. I mean, when you are doing a two-sample t-test, you're assuming that the residual covariance, the residual variability beyond. So basically, you have these subjects and you have these controls, and you are kind of like drawing a line, like a horizontal line across all subjects, and another horizontal line across all controls, and another horizontal line across all patients. And you're looking at the difference between those two, right? And you have like a cloud here of dots and another cloud here of dots, and you're looking at the difference that's a two-sample t-test. And the way to estimate where that difference is significant or not is by comparing the size of the difference to the size of the residual variability, basically how big these clouds are around those horizontal lines across all of the subjects compared to how big the two lines difference is. And that's basically what a t-test represents. It's the ratio of that difference in effect sizes divided by the residual standard deviation. When the assumption in this two-sample t-test is that the residual variability is the same across the two groups. So if it might actually not be the case, and it might be that the variability within one group is actually lower than the variability with the other. So basically what you're saying is that perhaps the cloud of points has more spread around one of the lines compared to the other ones, but that would not be the assumption basically of, or at least in standard t-test. The standard t-test assumes equal variances, so basically assumes that these residual errors around those, basically the distribution of dots around those lines, they have equal variances, they have the same spread. So basically you can actually use that same assumption that you are using anyway in the two-sample t-test to actually better estimate that residual covariance. If your sample size are relatively small, and you can just assume that the variances are going to be the same across all of the groups, and you can estimate a reasonable t-statistic within one group just looking at the average. But now instead of comparing at the actual spread around that particular line, you are using a little bit more robust measure for the actual spread by using those subjects to actually give you a better like a standard deviation estimation. So I don't know.
Would this only be if you were doing a post hoc?
Right. I mean, this is typically used for post-hoc analysis, right? When you already run your two-sample t-test and you determine that you found something significant, and now you want to display, well, what was the effect for one group and what was the effect for the other group? And that's
if you didn't find anything significant, then doing this you'd find things, but it wouldn't
right.
be anything meaningful.
Kind of just fishing.
Right. Okay.
Right. Exactly. If you don't find anything significant difference between the two groups, you can actually display those two activations, separate activations, like in two plots. But anything that you are seeing them as apparently different, it might be just a spurious effect of the thresholding operation, basically, or it could be difference in the power between the two groups. You could have like one group that has a lot of subjects and another group that has very few subjects. So when you look at what is significant in one group only, and then what is significant in another group, the group with few subjects is going to have less significance just because the power is reduced, not because the effect size is anything smaller than the other group. So there are many things that can confound you when you're looking at the difference between two groups just visually, and the way to properly do it and avoid all of these confounds is by running the actual test that compares the two groups directly, and only kind of like trusting the results that are significant at that level. Make sense?
Yeah. Sorry for.
Okay, so other questions with this experiment or this design? So all of that what we have looked is for one particular contrast, right? Within subject contrast. So you're looking at just novel minus learn. But I imagine that you might want to do this thing also similarly for different contrasts as well, or perhaps do like an interaction type of analysis.
I think that's it.
The design would be the same.
Yeah, the design is the same. Yeah.
Did you want to do like those two versus one another? I don't know why I'm trying to think. Like illegal learned minus legal learned versus novel. I don't know if that's a thing. Or even an interaction between the group differences and one of the contrasts. Like, is the illegal novel versus illegal learned different in the stuttering group versus the control group? You could also do that.
Actually, that's a good question, Alfonso. So, in one of the previous versions, you talked about looking at group difference for a specific contrast. Does that give us information about that interaction, or is that what you're?
Right. I mean, so could you pull back the configuration file for a second, and I can show you in there. Right. So, well, this particular one is looking at the. Right. It's looking at. Well, let's look at the actual difference. Let me see. Right. Difference between controls and patients. This is already kind of looking at the interaction, right? You are looking at the difference between novel and learn, and asking the question of whether that difference is difference in the controls versus patients.
Right.
You could have done something like this. You could have gone here. Let me see if I can do that with the mouse. So I assume that you have something like this also defined, right?
Right. Yeah.
As individual contrasts. And then you could specify here something like, yeah, I have to do this through the mouse again. Sorry. This. So you could have also done something like that, and that would be actually exactly the same. That should give you exactly the same results up to the same p-values, the same t-statistics, everything exactly the same as the previous one. So you are saying, I'm looking at this condition, and I'm comparing it to this condition. When I know whether the difference between those two conditions is actually different in the control versus patient. So that's another way to perhaps a little bit clearer to show. To do this type of interaction analysis, and they will be exactly the same as what we were doing before. When you run this type of analysis, what is kind of happening behind the curtain is that SPM is actually computing the difference between these two contrasts for every individual subject separately, and then it's entering that into another second level analysis where you are modeling only subject effects. So effectively, basically, you end up running exactly the same data through the same analysis in both cases. So this is already like an interaction, right? When you do, instead of this, something like all subjects here, instead of control and patients, just enter all subjects, and for the contrast between, just enter a 1. Then you are doing the main effect of novel minus learned, right? If you're thinking this as a 2x2 ANOVA, where you have within subject effects that correspond to the novel versus learned, all of these conditions, and then you have between subject effects, which correspond to these groups, controls versus patients. Then you have this type of 2x2 mix design mix, because you have both within and between subject effects, and you could look at the main effects of any of these things and the interaction between the two factors in a typical ANOVA type of fashion. And this is basically what we are doing here. This particular analysis is actually the interaction of the two factors. Make sense?
That makes sense.
But I don't know, do you have any additional conditions that, in addition to novel and learn, do you have other conditions that you might care about that you might want to also include in I'm just fishing here to see if you have any more complex type of a scenario that I may.
No, those are the two main ones that will be script.
Okay, and the same thing. So the same thing that we said for the control and patient, and then whether you want to look at those different, and whether you want to just look at the actual difference between those two, and only trust anything that is significant in those results, and then do post-hoc analysis for this, for those individual groups, applies to the individual conditions, right? You could actually just look at the novel minus baseline and look at whether that is different between controls and patients, or look at whether that activation in novel compared to baseline is what is the average effect across all of the subjects in that, and then look at separately at some set of analysis where you are looking at only legal learned condition and looking at minus baseline, right, and looking at whether that activation is, what is that activation on average across all subjects, and is that activation different between controls and patients. Or you can do like what we are doing here, looking at the difference between those two. You are looking at the difference between novel and learn, and looking at whether that difference is itself different across all of the subjects. So the same thing that we said for the two groups applies here. If you find anything that is significant here, you typically want to go back and try to display the individual results for each individual group, and also the individual effects within each individual condition, in this case, basically for each contrast. You want to know what happened in the novel condition and what happened in the learned condition to figure out what is it that is, what difference is it that between these two conditions in activation, is it that is causing that difference that is actually different between the two populations, between the two subgroups, right? So you want to display kind of like four things: novel activation, learned activation, both for controls and patients, and interpret that to interpret your results. Make sense?
Mm-hmm. Okay. Just one final question. I ran second level for the volume based with the subcortical mask. I'm going to have to go back and redo it based on what we've just discussed, but I'm just curious, like when I want to view the plot, I wasn't sure how to look at the subcortical structures in the plot.
Right. Typically, you want to use the slice display for that. Elaine, were you creating some, I don't recall the status of this, but I seem to recall that you were creating some scripts that will actually do all of this display thing
right.
from the...
I actually have both of those created. So I have a surf show one for cortical display and a slide series one for subcortical. They are pretty much ready to be shared with the group. The only thing I was hoping to add in was for the one, so when I generate, I pull in the results.image file that has the threshold activation, right? Mm-hmm. And I was hoping to include the statistical thresholding that's selected. So in like the file name, just so that there's a firm record of it. And you had added this to the header information.
Oh, right. And I also, right, I didn't do that for the surface, right?
Right. And for the volume-based, most of the information is there, but not all of it. So I think...
Yeah, I also noticed that the problem is that the script field in the Nifty convention is limited in number of characters. So what I did is that I'm also creating now a JSON file with the same name as your Nifty file, and that contains the explicit thing that doesn't have any limit in number of characters. So that contains all of the details of that. So when you are creating these mass files, just look for the same name as your actual Nifty file, but it will have a JSON extension, and it contains something that is called description, if I recall correctly, that has all of the information there without any cropping. That cropping I cannot change because it's kind of like internal to the Nifty definition itself. So I think it was better off just creating a different file.
So have you've added those already to the JSON files?
Right, I added that, but only for the volume level. I still have to do that for the surface level stuff.
Okay, so if you can do that and then let me know once it's ready, then I'll update my script to pull it, and then I'll share that with the group. And I've set up the scripts in a way that they can be used on any of the FL studies. So you just put in the study ID and then it will work. And feel free to copy them over to your own directories and edit them so that the plots look how you want them to look. But it'll be a good starting.
Excellent. So if you don't mind, I think I will send me that information, and we will try to incorporate it as part of FL itself. So I have an FL subcommand that basically invokes this and creates the plots from your results. That would be fantastic.
Okay. Cool.
If you are fine with that, are you fine with sharing?
Yeah, no.
Proprietary issues?
No, definitely not. It is 90% Alfonso, and then 10% I've just wrapped it in a couple of lines of code. So.
Well, fantastic, excellent. So just send me a link as well to the code, and I'll figure out how to basically merge it and put it together with the FL scripts.
Okay.
That would be great.
But I think it might be useful here.
Yeah, but at least visually, I mean, when you have this type of display and you want to look at the results, there are I would, if you only have subcortical stuff, I would typically plot the slides display, which is the kind of like third, it's kind of like in the middle of that one. So basically, you are looking at the results, but only within that mask, and then you can just right, and you can move this around and change. Yes, exactly. You can play with that to show multiple slides, and you can change the number of slides, and you can print it all. Do whatever you want.
Like, how do I know what lobule I'm in the cerebellum?
Right. Okay. That. Do we have a mask for that? Let me see. I think it does. Let me check. I'm not totally sure, but I think it does. Can you uncheck the multi-slice display just for a second? And go a little bit below that. So move the slider down to reach the cerebellum a little bit. And then click on anywhere in the image to see. I'm trying to see whether you'll get a label there. No, you get the coordinates, but it doesn't give you a label, right? So you just get the coordinates of the individual voxel. I mean, if you can tell from the anatomical kind of background image where you are, that's fine. Otherwise, we will probably need to kind of like.
Alfonso, in the not in the pop-up GUI, but in what Matt is pointing at right now, does that include?
Right. That has information about the individual, but since this cluster is so large, you are just finding pretty much everything. But if you find like a small cluster, it will be listed here below, basically the location in anatomical terms from that cluster. And the anatomical convention there that it's using is this Harvard-Oxford Atlas. So basically it has all of the cerebellum broken down into these 9 or 10 sub sections. So, but basically for this cluster, since it's so large, basically it's telling you that it kind of like overlaps with pretty much everything in there. But when you find a result that is a little bit more limited in scope and in space, it will give you a more precise anatomical location for it as well.
Right. So this is like a printout of all the areas that show activation.
Right, exactly. And you can right click on that and export it to a file, that information.
Oh. Can you just click on that and see? Okay.
And if you had multiple clusters, in this case, again, you only have a single cluster, but if you have multiple clusters, they will be listed here in the window a little bit above that. And when you click on those, you can also click on each individual cluster and look at the regions that correspond to that particular cluster instead of all of the suprathreshold results together.
Because I'm just like, what do we have to report in the paper? Like, do we have to like give that whole list and give like all the coordinates? Or, like I don't.
Well, for speech-minutes baseline, you would probably.
I mean, for that, like,
but like, yeah, you would probably give the ROI, which is basically listed on the bottom there, or where the peak of the ROI. I mean, sometimes they list like all of the ROIs that are included in that cluster, and then they give like an MNI coordinates of like the peak. Sometimes they just give like the ROI where the peak was. It kind of depends. That might be something for Jason to.
Right. The coordinates that are listed here, those are the actual peak coordinates within each cluster. So when you have multiple clusters, you will have multiple lines, and each of these coordinates at the left in each line basically tells you the peak coordinates of each cluster. That is sometimes what people report. Yeah. But again, for this particular result that you're looking at, it's basically just too large of a cluster, basically. So it's a little bit difficult to report. I would just summarize something like this, using a list of regions. But when you have a little bit more concrete or smaller clusters, then it makes a little bit more sense to describe them just by the MNI coordinates, right? Because it's a relatively small blob around that coordinates as opposed to a very big cluster that covers half the brain.
Okay, that's helpful.
Would it be possible to go over thresholding, acceptable thresholds, and that sort of thing? And could we use my data as an example?
Yeah, perfectly.
So I've run second level analysis on the volume. I did the whole volume based analysis, and then I also did the surface based and then a subcortical version of the volume. So I feel like it'd be best to, at least for right now, only look at the surface cortical results and then the volume subcortical results. Does that seem?
I mean, Jason, in my conversations with him, the surface-based analysis will just, it's just better in terms of like how the smoothing is done. It'll have more
Right.
Yes. The nature of the smoothing. Like it will do like each individual.
I also removed the AR1 covariate from the first level.
Excellent, perfect.
So you ran everything. So the well, okay, let's do the main effect of rhythm. So just this is rhythm minus normal speech across all participants. So right now I'm noticing a few things. So there's a couple of like interesting, the options here are not quite as complete as in the volume analysis.
Yeah, that's, I dislike this GUI as well. I'm in the process of making the other GUI, the volume level analysis GUI, to actually support surface level data, basically, as opposed to trying to improve this GUI, which is going to just duplicating a lot of code. Gotcha. So I'm hoping that in a few, but that's kind of like in the, I don't know, it's still going to take me a week or two to get that basically finished. But when that happens, basically, you will have pretty much the same thing. Because it will actually be the same code in both cases.
So I think like normally we would have like a vertex level P uncorrected of 0.001.
Right, and then you need but you need to apply. So basically, surface level statistics don't come in the parametric style. So basically, you need to run non-parametric analysis, which are this randomization analysis, to be able to get the statistics out of that. And that shouldn't error. Okay.
So, yes, this is one thing I was running into, is that if I wasn't CD'd into the second level folder,
that's weird.
It didn't detect it. So
I'll fix that. That is a bug.
So like I can go to now if I do the same thing again, it should work.
Okay, I'll fix it. Yeah.
Usually this takes like...
Yeah, that takes a few minutes. Sometimes it depends on the size of the data and everything, but basically it's running like a permutation test that is actually like a residual randomization. It's called analysis. Basically, it's generating random data and applying the same type of analysis that you are doing here to kind of estimate the size of the cluster that you would get just by chance. And then it's going to compare the size of the cluster that you get in your actual data results compared to this size of the cluster that you get in this random scenario type of case to determine whether they are significant, each cluster or not.
And
And it's going to do that based on both two measures, both size and intensity. The intensity is this combined measure that combines the size of the cluster and also how strong the individual voxels are, significant, the significance of each individual voxel is within that cluster. And that is typically slightly more sensitive than just the individual, the measure based purely on size. Because if you, sorry, go ahead.
Sorry, when you choose cluster level, P FDR corrected, that's taking into account both spatial and, or is that doing the weighting?
Right. I think, well, I have to check the code. In the other GUI, it will give you the option to choose which one do you want. Do you want to use the size or the intensity? In this GUI, it might be that it's just giving you not the choice, and it's assuming that you are using the intensity one because that's the most sensitive.
I think it might actually help now to maybe I'll just pull up the volume version and we can just kind of talk through stuff and that.
Right.
That'll be a little bit easier to.
Yeah, I mean, I haven't played with that GUI for a long time, and the reason is because I'm really working on replacing the GUI entirely. So I might have some things of like backwards compatibility with some other changes.
Let's see this. Let's do this. No, I didn't do that analysis. Let's just take away this one. So here's the rhythm minus normal.
Perfect.
Across all subjects, and so in here, so this is like an example of these are the three different clusters.
Right, and when you select each of clusters, you see that the kind of like bottom list changes, so that describes only the anatomical locations corresponding to each individual cluster.
Right. Okay. Yep, exactly. So, and kind of by default, it looks like when this gets loaded, it's the P001 P uncorrected,
right,
in the cluster level 05 PFDR corrected.
Yeah, that is a typical kind of like a standard setting, and that is basically valid. The combinations that are valid is anything that is corrected at the family-wise level, so basically either FDR or family-wise error correction at the cluster level, together with high thresholding that is not necessarily corrected, but it's at least 0.001, is considered perfectly fine. And if you want to use like a higher threshold, uncorrected threshold, like 0.01 instead of 0.001, then you need to use non-parametric statistics because of this whole thing. I mean, this used to be perfectly fine before, but then this report came that showed that this can like inflate the amount of false positives if you do exactly this, what we are doing right now. So instead of doing that, you need to change parametric to non-parametric statistics when you use this type of a little bit more liberal analysis, and that will run this permutation or randomization analysis to determine the significance level. You can, that only takes a few, it doesn't take much, just run at least. Yeah, let's see. Oh, it's still giving
I'm the wrong directory.
I don't know why this is happening now. Well, I know why it's happening. I just know why I haven't seen it before. No, it's going to a file too small.
So. But it is valid if you do this non-parametric. Because when you lower the voxel threshold, you get bigger clusters.
Right. Exactly. I mean, it's a measure of sensitivity, right? I mean, if you don't have too many subjects, or you don't expect the activation to be very strongly localized, but you expect a little bit of a more spread type of activation that is perhaps a little weaker, but it's spread over a relatively large area, then it's going to be more sensitive to use relatively high thresholds as opposed to lower thresholds in both cases. But for those cases, you need to run non-parametric because of this issue with parametric statistics when you are using a relatively liberal threshold. But yeah, I mean, assuming that you use, so just to simplify, if you're assuming if you're using non-parametric, which is valid any for the whole spectrum of cases that you might want to run, if you're using non-parametric statistics, then the choice of the height of the voxel level threshold is just a choice of that changes the sensitivity. It's always going to be valid. It's always going to be appropriate, and people are going to accept it as appropriately corrected and significant results. It's only affects basically your sensitivity to detect some particular type of effects. The type of effects that are going to be, your analysis are going to be more sensitive to if you use a very conservative threshold like 0.001 are things that are relatively localized and very strong. And the type of effects that are going to be more sensitive to your analysis if you use a lower threshold like 0.01 or something like that are going to be like relatively weaker but spread over relatively larger areas type of effects.
Okay.
So a little bit depending on your expectation of what you are looking for, you try to adapt that to maximize the sensitivity to those type of effects.
Okay. The other thing was that if you're doing a separate surface and subcortical volume analysis, okay, so here's the result of this. So there are these humongous clusters.
Right.
But so you couldn't really say where in this area, it just means somewhere in here.
Right, exactly. When you have this type of very large clusters, you typically report them as a cluster covering this area, and you cannot go into too much detail into the specifics of the individual subparts. But that's what you're doing. I mean, you're using a relatively liberal threshold at the voxel level because you're expecting to have large areas. So that's what your results are going to show you.
Okay. So if we go back to kind of the original threshold, if I'm doing, so this is looking at the volume analysis. If I'm doing a separate subcortical volume analysis and surface-based cortical analysis,
right,
would the correction that you'd make, because you're doing two different tests, would that come at the cluster level or the voxel level?
I mean, if you want to be really conservative, you need to apply a multiple analysis type of correction because you're doing 3 analyses instead of 1, right? And it's
3.
Well, you're doing surface level, volume level, and subcortical analysis.
Oh, well, I wouldn't include both the volume and the subcortical volume.
Oh, okay, so then just 2. Okay, so if you're doing 2 set of analysis and you want to correct for that, you would need to do a Bonferroni correction, and yeah, it will show up exactly there. Basically, instead of doing a 0.05 at the cluster level, use a 0.025 at the cluster level, and that will be fine. Yeah.
Okay.
But that is rarely used. I mean, this is the recommended and kind of best approach, but almost nobody actually does this type of corrections. At least in publications, as I've seen.
And would it not make sense to do it at the voxel level?
No, it doesn't. I mean, the voxel level threshold only kind of affects sensitivity, but it's not affecting the actual expected number of false positives. And what you want to correct is actually the expected number of false positives overall over your clusters, which are the things that you're going to be reporting, right? So the idea behind all of this is that you're doing this analysis which combine a high threshold and a cluster level threshold in order to to do a statistical test that make inference about the individual clusters that show up. So basically, when something is significant or not, it's going to be a cluster which is significant or not. And that's when you want to correct for false positives, you want to correct for potential presence of false positive clusters, right? So you want to know, like, I have a 5% chance of finding one cluster that is actually a false positive, or if across all of the clusters that I'm finding, 5% of those are going to be false positive. That's like an FDR type of correction. And at the level at which this happens is at the cluster level, and that's why the correction is needed at the cluster level. You're doing FDR across cluster, or you're doing family-wise across clusters. So voxels is only used as a way to actually define clusters. It's sometimes called the cluster defining threshold, because it's only used kind of like implicitly to define where a cluster is, and then you have this other method to determine whether those clusters are significant or not, and how to correct for potential presence of false positive across those clusters.
Gotcha.
Make sense?
Yes. Okay. So then, okay, so that's the correction. So then the other question I had is that, so under the voxel threshold, there's also an FDR correction at the voxel level.
Yeah. That is almost never used any longer. That used to be a commonly used option before, but then it came like topological class FDR came along and kind of like remove this option. So this is basically a voxel level FDR. So you are doing FDR across all of the voxels. And when people use that, at least in the past, they use it without any form of cluster correction. So you just do, in this case, you just use like 0.05 FDR corrected at the voxel level and no cluster correction at all. And that would actually be a significant thing for each individual voxels. But then these guys came along and say, well, this is not a good idea to do a correction across voxels, even if it's a FDR, because what this is telling you is that the 5% of the clusters that you are seeing in these results are going to be false positive. The problem is that you're not going to be making inferences about individual voxels. You're going to be making inferences about clusters. And it's going to be a much larger proportion of clusters which are actually false positive. The probability of a cluster being a false positive is much larger than 5%, even though the probability of a voxel being a false positive is only 5%. Because you get a lot of small clusters and a few large clusters, and it's very likely that the large cluster is the significant one, and the small ones are not just spurious. Then imagine that this is what is happening here. Basically, you have like 90% of the clusters that you are finding are actually probably spurious results, even though you are correcting at the 5% level in your FDR correction. So that's why topological FDR came along, and they say, well, if you're going to be making inference about clusters, you need to do like correction for multiple comparisons at the cluster level and not at the voxel level. So that's why this option is almost never used now, because this is actually doing a correction at the voxel level using this false positive control. But that's not how it's effectively used when reporting the results. So it's not recommended to use also for threshold.
So I noticed, though, that even with that FDR correction at the voxel level, if you do a cluster correction as well, sometimes it even gives like more results than it would if you do just a non-corrected 001.
Right. I mean, it could be. I mean, an FDR correction of 0.05 is probably slightly more conservative than a 0.001 uncorrected voxel level. So it's just a choice. It's just a matter of sensitivity again. I mean, what you are doing is basically changing the threshold of the voxel level, the cluster forming threshold. So you are most likely just focusing only on the very, very strongest of effects. So you're going to be making your analysis most sensitive to small clusters that are very significant. And sometimes that may be actually what you have in your data. So in those cases, it's a good thing to have done that. But you have to do that kind of like a priori. You cannot kind of fish around and find the actual thresholding at the high level that gives you the best results, because that's just increasing your chances of positive overall your analysis.
Okay. So I guess to that point, it's best to come up with like a thresholding scheme beforehand and see. I mean, I know there's like exploratory, you say like, oh, nothing showed up at this very strict threshold. If we lower the threshold to something else, we get this is a potential. Like, is that a reasonable thing to do?
Yeah, I mean, many people do in practice actually do that. I mean, they just run the analysis at the default options, which are relatively fine for small localized effects, and if they don't find anything, they relax the high threshold and try to find where they find any kind of like more spread analysis. And as long as you are doing just those two versions of the analysis, you are only inflating your false positives by 2. And I'm saying only because, well, that's still an inflation, right? But at most you're going to be getting like 10% of error. It's only when you start doing this a lot and you're saying, well, what if I just use this mask? What if I just do a one-sided t-test because I think I have a good, and start playing with all of those options, that you are keep inflating your false positives, and you are going to end up finding something that is significant for reporting purposes, but actually not significant truly. So when you go and try to replicate it, it doesn't work. So it's why all of these things is not recommended to be used, because even though, but it's a difficult sell, because I mean, it's what you, sometimes people do this and they will get a publication out of it, right? Because it's the way to get a significant result. And the whole emphasis at the publication level on the results that are significant is kind of like driving this thing. But then the problem of finding something that appears to be significant but wasn't truly so is that when you go and try to replicate it, it doesn't work. So you're kind of like shooting yourself on the foot. So I typically don't. I don't know. Most people won't recommend to do that type of fishing anyway.
I think on that point as well, it's like, so obviously you don't go and do 10 different versions until you find something that's just not clients.
Yeah.
But if you do, let's say 2, which might be reasonable, I think, what's really important is that you report that that's what you
Exactly. As long as you report it, it's perfectly fine, because if you say these are the analysis that I run, this is what I found, and then it's fine. I mean, everybody understands that the actual level of inflation that you are kind of like incurring when doing multiple analysis. It's only when you don't choose to report it, only report the thing that actually show up as significant, as if it was the only thing that you actually run, where you are like kind of like lying to yourself and to your, I don't know. Yeah.
And then one other question I had, which is how to, if you're comparing 2 effects, is there a way to say like, okay, within this cluster, what were the relative levels of those effects? So like,
right, yes. I think it's happening already kind of like automatically, but I'm not totally sure. So if you click on the plot that has these bars, like error bars, yeah, that is supposed to show you that basically it's going to show you the data within each cluster. So just click OK on that. That allows you to basically, those options allow you to change where are your clusters and what are the measures that you care about. In this case, well, in this case, you were looking, what was the analysis originally? So basically, the 2 plots in here are for the 2 clusters, and this is the...
Right. So, but is there a way to plot rhythm versus, like, see what it is in rhythm and see what it is in normal? Or
right, there is. I mean, what you would do is basically run another set of analysis where you're looking at the rhythm alone and the other condition alone. And then I use this same cluster. So basically, if you close this window for a second and click on the button again and look at the prompt that I told you to just forget about and click OK. So instead of that, yeah, you can select there a different SPM. Just saying, I want to look at these clusters, but I want to look it on these other measures that I computed in. And so you can do that by selecting a different SPM mod file, for example. Or you can just look at this data, but from a different cluster, right? And you can just change the cluster definition instead.
It would be great if you could plot those 2 things together, either, or at least know where those do those individual numbers, those effect sizes.
If you wanna plot them together, there is a trick for that. This is perhaps not the most efficient way, but it's a trick. If you actually run a second level analysis that looks at the presence of effects in any of the 2 conditions, so basically. What was the 2 conditions that you were actually entering?
Normal and rhythm.
Normal speech and rhythm speech. Okay, yeah. So if you enter those 2 conditions in the contrast names field, right? And in the contrast, instead of looking at 1-1, the within subject contrast, or contrast underscore within, instead of entering a 1-1, you enter a 1001. So basically, you're asking the question of whether are there any effects in one or the other condition, instead of looking at the difference.
Oh, 1-0.
Well, that analysis actually looks at both measures together. So then, even though you don't look at the results of that analysis, that SPM.mat file that it creates is the one that you select here. And then it will show you, in this case, 4 bars. It will show you the 2 bars for one cluster, another 2 bars for the other cluster. And each of the 2 bars will be the 2 individual conditions.
Okay. And then I think, yes. And then another, the interaction between a between subjects contrast and a within subjects contrast. You would just have to calculate the simple effects of...
Right. I mean, this type of plot will give you those 4 things separately, basically. So that will be like an interaction of the between subject, which in this case are the... Oh, no, because it will be a... right. It will... Let me remember. I don't recall. I think it will give you those, because in this plot, we are just looking at the difference between 2 groups, right? Or not?
This is across all subjects.
Right. I think when you have the difference between 2 groups, it gives you like 2 plots, 1 for each group automatically. You don't need to do anything like that, basically. I think, but I'm like 95% positive that is the case. So if you had entered 2 groups and you are looking at the difference between the 2 groups, this analysis will show you 2 bars within each cluster, 1 for the one group and 1 for the other group.
Can I check that?
Yeah, check that, because I'm still 5% unsure whether that is the case or not. I think so. And the reason is because what I think that these bars are plotting are the actual beta coefficients rather than the actual contrast values. And the beta coefficients are computed separately for those two for those two groups, or at least assuming that you use dummy coded groups, right?
Yes. Yeah.
Right. So it should do that.
Let's see what it's called. Run away. Okay. I do like group all. So I think this is both conditions. This is an overall effective group.
Cool.
I didn't find anything, but just like
okay.
but if I like just for
Yeah, just for plotting purposes, if you
Yeah.
just lower that threshold.
yeah.
Right.
So
You have those three clusters. If you click on that, that should give you, just click OK and there. Yeah. And that should give you 6 plots, I think. 6 plots, not only 3. Huh. That's unfortunate. It needs to do fix size. Okay, I'll check, because I was under the impression that that should show you the individual effects. And this design, you encoded it as two, basically you have 2 columns in the same matrix, right?
yes. Correct.
Okay.
I'll double check that.
Yeah, I mean,
Oh.
I'll check that.
Yeah. Okay. Yeah.
I mean, in the meantime, if you don't want to wait until I fix that or give you the option to do that, another way to go around that is the same trick that you use for the multiple conditions. You can create a design matrix that instead of entering 1 minus 1 for the difference between the 2 conditions, create another set of analysis that looks at the 1001 effect across all the 2 groups. And then when you look at these clusters within those other analyses, it will show you basically 1 per group.
And are those beta values saved somewhere for each of those clusters? And
within each cluster, no, within each cluster, you can.
Because it would be great if you had like the results, and then you could just pull it out and manipulate
Right.
however you want.
Right. No, I don't think they're safe. I mean, you can manually do that. So when you have let me see if when you have this window, I can click.
Yeah.
When you click, go ahead and click on the results window again. The GUI that we were looking. Yeah, in that one. When you click on the error bar, the bar display thing, one of the options itself is to show the Rex GUI. If you click on that, that gives you basically additional options here. And one of the options after you is to actually save the data into some format. So you can say, I want to save output files that have the average value within each ROI or something like
Oh, okay.
that. So you can kind of like do that manually within this GUI, but you're right that it might make sense to just create an external file with this when you display these plots automatically, because it's reasonable to do so, basically, at least only when you display this type of bar plots.
I mean, this is fine. I just wanted to know how to do that.
Right. Okay. So manually is that basically you can select which type of file you want to create, and whether it's a text file or a math file or something different. And when you click on extract and then results, it's going to create that file for you, basically.
So if I just click on
first, you have to click first on extract, just to extract the actual values for each individual subject across all of those clusters, and then you can click on the on results just to look at the actual statistics. That button, which is basically what you were getting before without all of this interaction. But now a file has been created, and if you look at the bottom, it says location output ROI file is something. So basically, it has created these files for you that have all of the raw data within each cluster, so that you can display it and do whatever you want with it.
Gotcha. Just wanna see what that looks like.
Yeah, and if you select the one that says save Rex file, the Rex is the name of the software that does this. That also creates an additional math file that contains the t-statistics and the p-values and FDR corrected p-values within each cluster, in case you care about those as well.
doesn't want to do that.
Oh no, that's just the cluster. So where's the other file then?
Oh, or maybe is there?
Yeah, because that's the coordinates. Now you want the output data file, the one that is called.
No. Oh, this one.
Yeah, exactly.
No, no.
.mat file.
Yeah, either .mat or .text. Both of them have the same information.
It's the cluster, the individual cluster.
Yeah. Yeah, and I think it has a spaces that name, so just put some single quotes around the name. Yeah, that's perfectly fine. Just paste it. Yeah. Okay. So let me see. How many subjects did you have?
Oh, there's 31.
Okay, so that should be. Oh yeah, and then I don't know why it's separate. It's basically one. I think the mat file maybe just have all of the clusters together. So basically, this is for that particular cluster. This is all of the data for each individual subject, right?
Oh, right. You can't do that. Yeah. Load.
And it only has the data for one individual, for each individual ROI separately. So basically, it creates a different file per cluster. But if you, instead of the, remember when you select the options to specify what type of files you want, if you have an option that says something that is called save rex file, that saves an additional like single mat file that is called rex.mat, and it's in the same folder as your second level analysis, and that contains basically all of it kind of like together in a single mat file. So,
Okay.
yeah, that thing, the rex, the one that says the option that says save rex project and output files instead of output files only. Yeah. So now, in addition to these output files, it also creates what is called a rex file, and rex is going to be just a .mat file that contains all of that for you. So if you click again on results, for example, okay, and I think that it doesn't tell you that it created that. I thought it should have told you. Okay. Well, could you just look quickly in the same folder that that your second level analysis is, whether it has created that file? I thought it will tell you, but so yeah, in that file, just look for mat files.
Rex.mat.
That Rex mat file, yeah. So I think the results are called, so that is going to have a variable that is called params, and instead of params, there is going to be a field that is called results. So params results contains probably all that you want. Let's check.
Oh, okay.
So you have ROI data that contains all the data for each individual subject across the three clusters, and then you have results that contains the actual beta values within each cluster and the confidence intervals and the statistics and all of those.
Oh, that's great. Great.
And this is the same format as what you get when you run ROI analysis. Actually, when you run ROI analysis, you also get this type of rex.mat file that contains all the details of your statistics for each individual ROI. It's only that in this case, the ROIs are defined basically by these voxel level analysis clusters instead of being defined a priori.
Okay. Cool. I think that's all I do.
I think that might be all of our questions for today, unless Megan, you have any other ones.
Megan's asleep.
Sorry, no, I'm not asleep. I just left it on mute. I promise. No, I think I have to redo some stuff with the correct spelling of things and then go from there.
I'm the same. That I have a few things to implement in terms of the ROI based analyses that we discussed yesterday. and I probably need a few days just to catch up on a few things.
Yep, that sounds perfect. So,
Set another meeting for next Tuesday, maybe.
yeah, we can organize pretty much the same time next Tuesday. Let me check actually. Do you prefer the mornings or the late evenings type of things?
I nominate the later evenings, but that's a little selfish. Actually, morning's good too. Morning's probably better.
It doesn't have to be like 6 a.m. morning for you,
Right.
Megan. I don't have any. I can meet anytime next Tuesday.
Yeah, I don't have anything as well. I can meet pretty much any time on Tuesday.
I'm free anytime.
Okay. Well, do you want to say 11 so it's not 6 a.m., Megan?
11. Right.
6
let
a.m.
me-
is okay. It's, I'm only here for a little while. And also, I'm technically off work next week, so if I decide it's too early, I just won't join in.
Let me check. 11. I think this Sunday is the US changing to summertime or Spain is changing to summertime. I don't know. One of the two countries is changing this Sunday.
We changed a week or two ago.
Okay, so then Spain is changing this week. Okay, so that means that next week is gonna be 1 hour further, so it's gonna be 5 p.m. Right, and this is a Tuesday. I have to be done before noon on Tuesday, next Tuesday. Can we do it a little bit earlier than 11 then start, just to make sure that we don't run out of time?
Could you 10 to 12? Does that work?
That would be perfect. Yes, excellent.
Sounds great.
Sorry again.
Yeah, no.
No.
No
I
worries.
really appreciate you doing this, Alfonso. Anytime you
No
can,
problem.
I'm here.
Okay. So if you have any questions in the meantime that you want to ask, just send me an email, and otherwise we'll reconvene next week and continue looking at this second level stuff.
Okay, awesome.
Great. Thanks, Alfonso.
Thank
Thank
you.
you.
No problem. Thank you, guys.